Today I'm going to be talking about the future availability and challenges of mineral deposits. So this, I think, is going to be very applicable to group number 4 that we're working on together this week. But I also hope to talk about some topics that will be interesting and important for everybody attending this summer school. So I think there's an important question that we need to ask ourselves that has to do with what drives the demand of mineral deposits and therefore minerals and metals. So sometimes we forget the importance metals have had in all our history, all our development as society. So since the early times, 10,000 BCE, we have been using metals. Actually, the first one that we started using was copper, and since then it's still a very important metal. But in the end, the understanding of metals and their properties have triggered major technological advances that are very important for our society. I have down there a couple of photos. One of them are the Roman ruins of the Rio Tinto mine. This is one of the oldest mines in history, which was a large silver and gold mine in Spain that was worked by the Romans, and it was the first underground mine ever constructed. And on the other side, we think a lot about metals and computers and cell phones. Most of the talks we listen about critical elements and metals, those tend to be the main topic, how many metals are in our cell phone, etc. But actually, metals are also incredibly important, for example, for modern medicine. We wouldn't have modern medicine if we didn't have any metals. So in general, metals are an incredibly important drive for our society and our development, currently and also in the future. But development has its consequences. I think this is one of the main reasons why we're meeting here to talk about these important topics. Our development has required a lot of fossil fuel usage, and that has implicated a lot of release of CO2 into the atmosphere and our current problem, which is global warming. And this is something that we see every year getting worse and worse. So I flew in from Chile. It's winter over there, and we went from having extreme droughts to now having really heavy rains and flooding, and it has been very hard in a lot of parts of the country. And in general, we see extreme weather events, and that is all related to global warming. So what do metals have to do with this? Well, we know that the solution, or our current solution, how I like to talk about it, because there could be a new solution coming up soon that we still haven't thought about. But our current solution is the energy transition. So we want to move into renewable energy. We want to move into solar energy. We want to start using wind turbines. We want to switch to electric vehicles. But then we have to remind ourselves that all these need raw materials. They need metals to be constructed. Just for example, thinking about an electric car, it uses 2 times the amount of copper than a conventional car. It also uses lithium, it uses cobalt, it uses nickel, and it uses rare earth elements. And so on, we see not only more metals that are important for the energy transition, but also different metals. So we have a whole list nowadays of what we call critical metals. That means that the supply of these metals are critical for our society right now, but also for our future development as a society. So this is our current dilemma, and I like to present it this way because these are probably some of the most representative critical minerals, our critical metals. And if we see, for example, copper, which is, one would say, the most common one, if we wanted to achieve the whole energy transition, we would need at least 2 times the amount of copper that we have nowadays, that we have discovered, that are in the reserves of current mines, etc. We will need more than 5 times the amount of rare earth elements, and rare earth elements are a group of metals that are really important for making supermagnets, which are very important for lithium batteries and wind turbines. And then we move until lithium, which is the most extreme of these metals because of electric vehicles, and we need more than 40 times the amount of lithium we have nowadays in order to achieve the energy transition. So I call it the dilemma or the paradigm because one would tend to think that a more sustainable future is one without mining. And here we have a problem because we need these resources, we need these raw materials, and this implicates that we need more mining. So in that sense, in general, the demand of metals changes. 50 years ago, we were not talking about cobalt. We were not talking of rare earth elements that now are really important. And I like to talk about the example of rare earth elements because these metals, for example, 100 years ago, were not really relevant at all. They started being relevant in the 60s when the color TV was invented, because actually rare earth elements, it gives color to the screens of our cell phones and also the screens of our TVs. And the first one of these mines was started in the US. It was called Mountain Pass. And it was the first producer of rare earth elements used for the TV industry. And they were the main producers until the main 90s when China started producing rare earth elements. And in the end, the Chinese market took over the global market of production of rare earth elements. And in 2010, there was a big crisis related to the production of rare earth elements, which started with a diplomatic issue between Japan and China, which led to the global concern that it's not a good idea to have only one country producing a strategic group of metals. So in that sense, we see after 2010 that a number of other countries started developing rare earth element projects, and the demand for these metals increased and changed. All of this because of these super magnets that I was talking about before. And this is a map of the world, and we see in stars which are the active rare earth element mines. So these are active, they're producing right now. And we can see in circles projects that are going to be developed. So this was the effect after 2010. So this is how the demand of metals can change, and that can actually change the whole industry as a whole. So in that sense, when we think about mineral deposits, we have three main phases that we think about it as geologists and as mine engineers and as anybody who is related to the mining industry. One has to do with exploration. We need to be able to find new mineral deposits. And for this, we need a lot of knowledge. We need geological knowledge, because if not, it's basically looking for a needle in a haystack. So it's very difficult to find a mineral deposit. But then when we find one, it's just not finding it. We also need a way to operate it. So we need to evaluate the deposit. This means that we need to know the geological architecture of the deposit, and we need to characterize not only the main commodity, but also what byproducts can we find. For example, we think a lot about copper mines, but a giant copper mine like the ones we have in Chile do not produce only copper. They actually are the main producers of rhenium, and they're also very important producers of molybdenum. All of those are byproducts of a main commodity. And finally, exploration or evaluation of deposit is not really important or viable if we are not able to do a responsible exploitation. I think that is something we all agree here in this room. And this has to do a lot with the current concerns we have over metal supplies, and also conflicts that we have seen that have arisen, and historical conflicts that are related to the mining industry that I think we all need to be aware and are aware of. But how do we discover mineral deposits? That has also changed with time. I would say before the 1950s, we would use a classical way for mineral exploration. There was this person called the prospector, who was somebody that would walk around the mountains looking for specific rocks that could actually show that there is some kind of mineralization. They will bring the rocks to a mining company, say, hey, I have this great location. I might tell you where it is. We can do business together. So that was all working on surface, a lot of geological mapping. And from the 1950s on, technology advances. Now we know geophysics, we know geochemistry, and we can use that for mineral exploration. But in the end, one of the biggest drivers of how we find mineral deposits is using the information we already have. So if I have a mineral deposit that I know, the first thing I'm going to do is going to go and look around it. So that we call brownfield exploration, and it continues to be the most important way we find a mineral deposit. So I will use copper, because I really like copper, and Chile is the biggest producer of copper in the globe, and it's also a critical metal. So I'm going to be using copper as our commodity example for the next few slides. So if we look at historical discoveries of copper, until the mid-20th century, I would say the majority of copper deposits were kind of easy to find because they were on surface. So you would just walk around and find one, or even better, these were historical mines that were actually exploited or they were being worked by indigenous population. So for example, Chuquicamata, which is one of the largest copper mines in the world, was being exploited by the Incas before other big companies. So in general, our past discoveries are near surface, they're huge, and the grades were good. So these were great deposits. But what happened? So we were very good at finding these. Imagine that they're close to surface. We walk around, we take our samples as geologists, but then we see a big change around, I would say, 2009, and we started this new period of a drought of discoveries. We're not getting better at finding more deposits, we're actually getting worse. And if we compare that with the amount of money that is being invested in exploration, it doesn't really correlate. We actually invest a lot of money in exploration and we're not finding new deposits. So we have a big problem here because, as we remember in the dilemma slide, we need more metals. So we start looking at new discoveries. These are copper discoveries in Chile. There's a timeline, and in the y-axis we see that. So what happens and what we see here is that every time our new discoveries are deeper and deeper. So this has two problems. One is that they're more difficult to find, and two, they're more difficult to operate. And this is not only the trend in Chile, this is a global trend. In general, new discoveries tend to be deeper. And also exploration, mineral exploration, tend to look for this brownfield exploration. So I want to look for deposits around an area where I know there is an existing deposit. So then we talk a lot about greenfield exploration, which means to find a deposit in an area where nobody else has looked before. So that's something that is risky for companies to invest on, but if you do it right, there's a lot to win around it because you are the first ones to discover a deposit in a new place, and there's a lot to explore around. So I always like the example of Oyu-Tolgoi, which is a massive, really big copper mine in Mongolia. And it's pretty recent, it's a discovery compared to other deposits. And the company that found it, they were the first ones to be there, to find a big deposit there, and that was a game changer for the company and for the country. So then we get to the question, and I get this asked a lot by especially non-geos because there is a concern, are we running out of copper? There is no more copper. We found all the copper mines that were to be found. Well, the truth is no, not yet. There are a number of things that we can do better and we should be better. I would say we have in our favor geology. Geology, there's so much to learn about it. And if we learn and understand geology, there's more to discover, but it's deeper. But then again, the other challenge is that deeper discovery are more difficult to operate. An underground mine is quite more difficult to operate and economically more challenging than a surface like open pit mine. And discovery is not the only control on supply. We need to remember that also. So we need to be better at finding deeper deposits. That means undercover areas. So we need to see past what we're walking on. So there's some places in the world that have been really good at this historically. I would say Australia as a country in a whole has been very good at doing exploration in undercover areas. That's mainly because they use a lot of geophysical tools. So for those who are not geologists, we talk about geophysics when we're trying to understand the physical properties of a rock. And we can actually see those physical properties by using these geophysical tools and see these properties under our feet, so underground. So for example, we can use seismicity, or if there is conductivity. So remember, if there are minerals with metals, these will be conductive in alarm, etc. So in general, Australia has been really good at this, and there's a lot to learn from them. But in general, we need to be able to develop better exploration tools. We need to think outside the box. So what has happened until nowadays, we use conventional tools. This is working mainly on surface. These are high risk, they have high cost, and that means that they're low value exploration. So as geologists, as exploration geologists, with the concern of finding new mineral deposits, we need to be able to develop different tools that will help us look undercover. So we need new technology, but also a way to lower the cost of targeting, and very importantly, be less invasive when we're doing exploration. Because nowadays, our society is very different as it was 50 years ago. So in that sense, I'm going to show a couple of examples of non-invasive exploration techniques, which I think are great. The first one is actually looking at the chemistry of minerals that can be associated to mineral deposits. So if one thinks about a copper deposit, it's not only copper-bearing minerals, there are also secondary minerals that we can use to vector towards where the ore deposit is. And these minerals can be way more extensive in how they happen, and we can use their chemistry as an exploration tool. The second one is that we can look at the chemistry also of trees. Trees that can grow over a mineral deposit that is concealed, because trees can absorb metals. There are great examples of, for example, eucalyptus that absorb gold and is used as a tool for exploration in other countries. Or, for example, ferns can absorb rare earth elements. So we can look at the chemistry of plants in order to understand if there could be a mineral deposit underneath. And finally, we can also look at the chemistry of the water. So all these elements will interact with mineral deposits and have some kind of fingerprint that we can actually try and understand. Or even better, we can also use our own geology of wherever we are and start to develop tools that are tailored for our location. So again, I come from Chile. We have a lot of earthquakes. We're probably the most seismic place in the world, and we're really proud about that. Don't ask me why. But there's a very recent study that was done by a Chilean university, which I think is also a great example of applied research, that is using seismicity, our natural seismicity, to imagine what rocks are in the subsurface. And this way, see if we can use that seismicity, for example, to target a mineral deposit. So this was a recent study that tested a copper deposit, and it was very successful. And now this research group is in a second phase where they applied for a new grant where they're trying to tailor a tool for mineral exploration that uses our natural seismicity. It's a great example of applied research, and again, it's not invasive. We're not drilling. So these are great techniques because we want to be the less invasive possibly when we're doing mineral exploration. But it's not all exploration, even though that's probably my favorite topic as a researcher, but it's also operation. How do we operate a mine, and how do we do it in a way that is actually has to do with how we work currently as a society? So we need to optimize operations, and in that sense, create processes or method that can improve the way a mine works. So I always show the example of MineSense. MineSense is a technology that was developed a few years ago. It's a shovel, so we need actually a shovel to get the material out of the mine. But this is not any shovel. It's actually a shovel that has an XRF included. And so XRF is a technique that will measure the composition of the rock that is on top of the shovel. So we trust too much our human eye when we want to differentiate between rocks that have mineralization or do not have mineralization. So this is a way of using technology to actually be able to distinguish if what we think has mineralization or not actually has it. So we optimize the process. And then we have mine and automation. And I think this is an interesting topic because for a lot of people it can be difficult because it means people need to change their jobs. They need to transition to learning new skills. Instead of operating a truck in person, you need to operate a truck from a completely different location. And there are mines that are starting right now to operate, which are completely automated. So there's a giant truck that is moving in northern Chile, but the person that is actually managing that truck, that's driving it, is sitting in an office in a completely different city. So this can sound scary, but it also has to do with safety. So managing a truck from an office is quite safer for the worker than actually being there in the mine managing a giant truck. And of course, all of these changes had to do with environmental sustainability. We can never forget about that. Autonomous trucks can optimize routes, Also, we can start working on reducing fuel consumptions and emissions. And there's a lot of examples of operations that have been changing all their trucks to electric vehicles or that use hydrogen. So these are the operation side of things that are changing and need to change and that are challenges. And then we have the problem of depth. So it's not only that discoveries are getting deeper, but also mines are getting deeper. And this is an example in South Africa. It's part of its Witwatersrand deposit, which I think I really badly pronounced, which is one of the largest historically gold deposits in the world. And we have mines here that can reach over 4 kilometers deep. And there are people working 4 kilometers deep. And that is harsh, it's hard. The temperatures are hard, the level of oxygen is hard. So in this sense, I would think that automated mining is safer for the workers in this case. But it doesn't have to do only with the workers, but also the challenge of how do you operate a mine that is that deep? Because rocks do not behave the same way near surface than 4 kilometers deep. They break in a different way. And it's not only these mines in South Africa that see the challenge, but for example, El Teniente, which is one of the largest copper mines in the world in Chile, it's underground and is reaching over 2 kilometers deep of tunnels. And it's not a small mine. They actually do block caving, which means blasting huge amounts of rocks. And they have had real issues being able to work that deep because they cannot understand, they do not know how rocks will behave. And there are no experts that they can ask because actually they are the experts on the subject. So it's another big challenge. But then, as I said before, discovery is not the only control on supply. So mining companies in general, when they talk about how much copper they have, for example, or any other commodity, they talk about their reserves. And reserves are basically what is proven that you trust that is the amount of metal that a mine or a deposit has. But there's more than that. We also have resources, or we have the true extent of mineralization. So in general, deposits are larger than what is formally informed. So in general, our resources, for example, for copper, will continue to grow over time coincident with production. So this is good news. It's not only discoveries, actually current operating mines tend to have more material and more resources than what is formally informed. And then there's another big issue, which is the discovery to production time problem. And it's called a problem, but I think it's a very difficult one to try and figure out, because from discovery to operation, so let's always remember we're thinking about this because we need more metals. For example, for copper, we need nearly 16 years between we first discover a deposit to when it's actually producing copper. That's a lot of time. And from what I understand, the energy transition is something that should be happening yesterday. So we have a real problem here. So in general, discovery, exploration, studies take a really long time. A lot of this time has to do with environmental permits, and that is good. We need that time. Also, some of it has to do with bureaucracy, that is unique for each country. But in general, when we think about the metals for the future, we have this issue, which is the time. And it's not only production, it's also processing. So we think about mining operations, we get the concentrate, but then we need to refine this. For example, we're not mining copper by itself. We're mining copper minerals, and by the end, we want copper cathodes. We need refined copper, and this requires smelting. It requires a lot of industrial processes that are energy consuming, and these are not democratically distributed around the world. And it's not only copper. One would think, for example, of rare earth elements, going back to that example. After 2010, we see more countries producing rare earth elements, but if we look at processing, actually nearly 90% of all the processing of rare earth elements goes through one unique country. So again, these are challenges because we do not want to monopolize the production of any critical metal for the future. But there are initiatives that are changing the future of the industry, and I think this is great because it tackles a lot of the issues that we are talking about this week. There's more than these examples that I'm showing here, but these are some that I think is important to know. One is the EITI, which is Extractive Industries Transparency Initiative. So this is a global initiative for extractive transparency. It has to do with including every stakeholder into how a mining works. Social groups will have information about extractive groups, and this is it's a country-based, so a country can subscribe to this initiative. And the second one is a startup that is now working in the US. It's an initiative to restore historical mine sites through reprocessing their tailings. So I'm going to process tailings, I'm going to get some concentrate of a good metal there, I'm going to sell that, and instead of making myself rich, I'm going to reinvest that in restoring the mine site. And this is a great example because it's an NGO, but it's working with the mining industry, specifically with Rio Tinto. So great examples of the importance of transparency and therefore being able to work on trust, and the importance of being responsible for our trash in the mining industry. And finally, we have recycling. So mining, the metals are not only those that we need to find in the subsurface, but also we need to be able to use and reuse those that we have with us. And I think this is one of the biggest differences with fossil fuels, is that we can recycle metals. You cannot recycle gas or any kind of fossil fuel. But less than 1/3 of the most important 60 metals that we use have over a 50% rate of recycling. And actually, of these 60 metals, there's 34 that are less than 1% recycled. So there's another problem here. And I like to show this because we think a lot about the mining industry, but we need to think about the whole supply chain. We need to think also how we make things. So nowadays, when companies make technology, let's think about cell phones, computers, they think about being more effective in how they use space, making it smaller and smaller, and of course, reducing cost. But it also should be in their thoughts to make things thinking about how we recycle the metals afterwards. The idea is not to have this really intense mining all throughout history. The whole idea of this energy transition is that we get the amount of metals we need for the energy transition, and then we recycle them, we reuse them. If not, we just will become another fossil fuel world, just using something different. So, and just not least important, but by the end, I like to always mention the social license. And I think there's going to be other talks that are going to talk about this topic. But our current society requires a social license for any new mineral deposit discovery and development. It doesn't matter what metal it is, if it is critical or not, the social license is a must. And I'm going to show and finish with a positive example. So a few years ago in 2019, it was announced, like a big news, that the first rare earth element deposit in Chile was discovered. Not in northern Chile, which is our mining area, but in actually central southern Chile, an area that has never seen mining before. It has had industrial development, but never mining. So what was the first reaction of the community? These are a couple of news clips. They're in Spanish, but the first one is from February 10, sorry, it should be, say, 2019. And it says, a new menace in the Bio, that's the name of the region. Mining rare earth elements in Penco. Penco is the locality that is just beside the mine site. And then in 2022, fast forward a few years of pretty, I would say, bad communication with the community and the company. In Penco, the local community, they celebrate that the project is leaving. So this was closed down in 2022. This project is very interesting because in general, rare earth element mines are from hard rock, and these can produce very toxic waste. Actually can produce radioactive waste because the waste has a lot of uranium and thorium. But this type of deposit is hosted in the soil. It's called regolith style rare earth element deposits. And it does not produce radioactive waste. It does requires a lot of water, and it requires taking out all the soil. And some other countries where it's done, they use in situ leaching, which is basically leaching the whole hill that has the soil and the resources, which could be have a very hard impact in the environment. And I was kind of, sad that the project was not going to work out because this is a game changer. We're having a new type of deposit in a different location. This is greenfield exploration in its best way. But it didn't work out because that current company was not able to engage with the community. But as an update, so this is a positive ending, after 2022, the project was taken over by a different company. And what they did is that they talked with the community, they consulted them, and then they asked them which were their main concerns with the project. And they found two main concerns. The first was lack of information. Most of the community was concerned about radioactive waste, which was not the case here, basically because there was no information. There was no engagement with actually talking with the community about what the project was going to look like. And the second one is water. The community was not going to accept that any mine site was going to use their water. Because believe it or not, in Chile, water is private. It's not a public commodity. And the company had the water rights of the local streams, and they could basically use all the water in the area. And this was a big issue for the community. So the company that came in after this consultation understood that in order for them to actually work and have this mine and make it operate, they needed to rethink the whole project. So what they did is that instead of having a waste-style mineral deposit, they invented a completely different way of processing that it's more similar to reverse osmosis, so kind of what we use to get salt out of ocean water. And what they do is that they take the soil, they wash it, and they recycle 99% of the water in this process. And the other 1% that is left, they use the gray water from the local community. And the waste of this is soil or clays that they work. They have a neutral pH, then they put back, and then they reforest all this area with native species, because before these are all forestry places. Okay? So this is completely different. And it's a great example. So they have actually engaged with the community. They have an open office where anybody can go there. They have changed the way they work. And the company is waiting for the last environmental permits to be accepted. That will probably happen at the end of this year. And if this happens, this goes into operation, it's going to be a game changer for the local community and also for the country in general and for rare earth element production. So this is a way of doing things differently, and also to show how important water is for communities. So in conclusion, the future availability and challenges of mineral deposits is a multi-layer challenge. It has so many different ways of seeing it. We have geological models that are really important, exploration methods, production technology, social license. So it's a multi-layer challenge that, of course, will have a multi-layer solution. And I think that has a lot to do with why we're here, and the diversity of this group is that the biggest challenges need diversity and need people from different parts and different professions to think about very creative solutions that are so important for such big challenges for now and the future. Thank you.